So when we try to integrate vector valued functions, what we find is that they behave pretty much exactly as we'd expect. When we have some sort of vector valued function which has component functions, then the indefinite integral of that vector valued function is simply the sum of the indefinite integrals of each component. So we take the integral here, and integral here. Now, if you remember from your introductory calculus that when we integrate a standard scalar function, that we get some sort of antiderivative of that function plus some sort of constant, right? That's how that always works. Is that the antiderivative is the same with except for some constant. So if we carry those constants through here, and we have a constant for the I component, a constant for the j component, and a constant for the k component, and then we do some algebraic rearranging, and we get the antiderivative sort of parent functions here, and we get these arbitrary constants, and we put those in like terms, we can separate them into saying that the vector valued function has a vector valued antiderivative parent function, and the only difference is some sort of arbitrary constant vector. So it's nice. It basically behaves exactly the way we would expect when we scale up the dimensions. And what we also find is that when we do a definite integral, where the value of this parameter goes from a to b, then we simply take the definite integrals of each of these scalar functions and those components, the values of each of these integrals is the component of the final vector, which will be again, that would be a numerical vector.